All right, I think it's time. So I was a little bit slow with these slides on the class theory. I will try to wrap up quickly in 5 minutes, and then we will go back to the usage lecture. Okay, so we are giving details about this task C, which is how to integrate the system of perturbation equation. We have seen the different approximations. Now, I would like to we already talked also about this polarization hierarchy. And I'm going back, sorry. That was. So going forward, another technical aspect when you integrate this hierarchy, this Boltzmann equation, is that it's a stiff system. And the best way to integrate a stiff system is to design a specific integrator called an implicit integrator. So we are using for our ordinary differential equation solver, we are using an algorithm which was developed specifically for class because it has all the requirements. It's not the Runge and Kuta solver that you may know. Actually, you have the option to switch a flag in order to use Runge Kuta. There is also a Runge Kuta distributed with class, but it's less efficient. And the main reason is that so we have a stiff system of equation in the early universe due to the baryon photon tight coupling. You know what it means? It means that there is an equilibrium which evolves slowly, an equilibrium solution which evolves slowly, and the equation forces the system to track this equilibrium with a very, very short time scale, a very large response. And so this is it's famous that this problem is difficult numerically. It leads to instability with most ordinary differential equation solvers, unless you use an implicit method. So the implicit Backward-Euler method is not the one you learn as the first possible method. It's a way to increment the, if you have a system of equation, which is a system of equation for y, and you have a differential equation, you know what y prime should be as a function of y, and you try to increment y at different time steps. At a first time step, you have a y of n, and you want to find the next time step y of n plus 1. And the usual forward Euler method that you know will say that yn plus 1 is yn plus a derivative times a time step. But this derivative will be evaluated in yn because you know the value yn. The backward-Euler method is known to be much more stable when you have a stiff system, much more efficient. It just amounts in using the derivative in yn plus 1. But you don't know yet what is yn plus 1. So to find yn plus 1, you are going to solve algebraically for this method. And if you have a system of linear coupled differential equation, this amounts in inverting a matrix in order to find a solution to the system. So the integrator we use is of these categories, and it's much more efficient for stiff system. So it has to do some algebra in order to solve this equation, but it does it quickly with some thanks to some tricks. It will always evaluate also the time step automatically. So as we said, if your cosmology is such that something happens, that will be detected. It has some other features, like the fact that the system is sparse. There is an S missing. It means that if you write your system of differential equation in matrix form, like y prime equal to a matrix times a vector y, there are lots of zeros. The Boltzmann equation tends to couple multiples between nearest neighbors. So you will have non-zero coefficient close to the diagonal, and then lots of zeros. And this could slow a lot the system unless you do something clever with it, some algebra. So all these tricks were implemented by Thomas Tram, and he obtained an integrator called NDF15, which is really the integrator of class. You are free to use it in other problems. I think it's extremely powerful. We even found that when you switch, you decide that you will never use the tight coupling approximation. You start from initial conditions and directly with the correct equations, the code can run through them easily. And that would absolutely not be the case with the Runge and Kuta method. Okay, so this was about numerical algorithm. At the level of the primordial spectrum, I already told you the subtlety is that you can choose between analytic primordial spectra or simulating inflation. Okay, if some people here are very interested in this and specialize in inflation, I can say more, otherwise I will skip. I want to tell you about a small technicality related to the calculation of the nonlinear power spectrum. So the default method in class is to use HaloFit. When you use HaloFit, what HaloFit takes as an input is the value of the linear power spectrum computed at different redshifts. So I show here a plot where you have K, and you have the redshift. This is the smallest redshift. Redshift goes up. And on each of these blue lines, you have an evaluation of the linear power spectrum as a function of K and at 1z. In order to find the nonlinear power spectrum, the code must find automatically for each redshift what is the value of the radius r such that the variance of fluctuation in a sphere of radius r is 1. This will give the redshift of nonlinearity, and it's a key step for HaloFit, and HM code uses something similar. So at small redshifts, the code is going to fluctuate r until this condition is satisfied. And when you find sigma, it means that you integrate the matter power spectrum multiplied by a window function, the top hat window function. And your sigma depends at the end of the value of the power spectrum, mainly in a given range of scale, from some k max to some k min. This is what I showed here in red. The code will find that at redshift Z1, R, sigma R is equal to 1 by integrating and picking up values mainly in a given range here around R, around 1 over R, because k is related to 1 over R. Then the code does it at different redshifts, but when you go up in redshifts, the linear power spectrum is lower and lower. So in order to get the point where sigma crosses 1, you need to go to smaller and smaller scales. And at some point, the code will realize that given the k-max in the code, the calculation of sigma cannot converge. So it means that the HaloFit method will not work. So the code will detect this and will say, okay, up to this redshift, I'm not able to use HaloFit. So I will set PNL to PL, because what else could you do? So it means that the nonlinear power spectrum computed by HaloFit will really have nonlinear values up to a redshift and linear values above. And the redshift at which this happens has been determined automatically and is given in the output. So you know that above a given redshift, nonlinear corrections were not computed. So in most cases, you will be happy with this because you want your nonlinear power spectrum only at small redshifts, say 1 to 2, and the code tells you that it could not converge above a redshift of 4, and you don't care. But if you care because you wanted a nonlinear power spectrum at higher redshift, you see what you should do. You should rerun class asking for a larger Kmax. Then automatically this method will work at higher redshifts, and you will get your nonlinear power spectrum up to higher redshifts. So the logic is really simple. Okay, and the last thing I want to stress is about CMB source functions. If you try to compare the CMB source function in common class, you will certainly find big differences. So if you studied CMB physics, you have all seen now the exact expression of this temperature source function, which gives the harmonic transfer function after convolution with the Bessel function. It has well-known terms, the Sachs-Wolf term, the Doppler term, the integrated Sachs-Wolf term, and the polarization corrections. Now, suppose that you want to try to demonstrate this formula from scratch, like, for instance, Matthias Aldariaga did many years ago. At some point, you will arrive at some intermediate stage where you have 3 terms. One convolved with a Bessel, one with its derivative, and one with its second derivative. And then if you want a simple expression like this, you should use integration by part. In order to integrate this once, integrate this twice, and then this will push some derivatives of S1 and S2 to the prefactor, and you will arrive to this expression. At a numerical level, this is problematic because you need to evaluate S1 prime, S2 prime, S2 prime prime. It's not so easy. S1 and S2 are combination of photon perturbation, baryon perturbation, and thermodynamics function. When you compute these derivatives, you could think that when you had theta b, for instance, the velocity of the baryons, you get a theta b prime. No problem. You have an equation giving you theta b prime as a function of theta b. It's the Euler equation for the baryons. So then you get a more cumbersome expression, but still nice and exact. It's not as simple as this, because when you have to take this derivative, you need to take first and second derivative of metric fluctuations coming from first and second derivative of the Einstein equation. And then you need first and second derivative of matter terms, like for instance, the anisotropic stress of photons, etc. And they are complicated to evaluate. You get very, very big formulas. And in these formulas, some of the terms have to be evaluated by a finite difference method, which is always inaccurate. So COMB uses this method of putting everything in this form, and the expression of this term were obtained by Mathematica and directly plugged into COMB, such that the source function that you find in COMB for the temperature is like this, and it didn't fit in my slide even. So you see, it's a big contrast with the previous formula in which you had like 6 terms. Now you realize that in fact to get these 6 terms, you need 20 lines of codes. And really some of these terms are not very nice. I remember the most infamous one is this one, the peak dot. The peak dot, I wanted to go through the same line in class at some stage. The peak dot is horrible. It's a derivative of the anisotropic stress of massive neutrinos. And to get it, you really need either extremely complicated equations or a finite different methods. So after seeing this, we decided to change strategy and to stick to this formula. This formula is nice because the S0, 1, and 2 are extremely simple, and you get them directly from your system of equations. And of course, you must do 3 convolutions, but in our case, it doesn't make the code slower. And these convolutions are with derivative of Bessel function that you get anyway for free. Because to compute the JL, you need to use some recurrence relations, and they give you the other ones anyway. So there is no drawback in using this, and we can stick to simple formulas. So when you derive your formulas like this, you find that S0 contains the Sachs-Wolf term and the integrated Sachs-Wolf term, S1 the Doppler, and S2 the polarization correction. Of course, I am still free to do integration by parts in order to move terms up and down from one line to the other. I told you I didn't want to do it before because I didn't want to get a more complete expression. But if I try to do it in order to get a simpler to evaluate expression, then I should try. So in particular, the problem here is that we have a psi prime, and the psi prime is not so easy to evaluate using the Einstein equation. So we decided to move this term, part of this term, to the right, to the S1 piece. While in order to increase accuracy and performances, we decided to move this term to the S0 piece. So what you get here is a compromise between simplicity and numerical efficiency. The Sachs-Wolf term is in S0. Most of the integrated Sachs-Wolf is in S0. The Doppler is in S0. S1 is a tiny correction corresponding to a very small part of the integrated Sachs-Wolf related to the difference between the metric fluctuations. This comes from the anisotropic stress of neutrinos and photons. And S2 is a very tiny correction too, coming from polarization. And all the terms here are extremely easy to evaluate from the integration over the differential equations. So this is the expression that you will find in class. And don't be surprised if it has nothing to do with what we saw before for COMB. Okay. and I think this is the last slide. Yes, it's the last slide of this theory lecture. So, do you have questions on this? If not, we will go on with the usage lecture. No question? Okay, so we will try to finish the lecture on how to use the code without modifying it. So I don't know why the number here doesn't work. I will correct it. We were at the point where we were describing all species in class, and I told you about cold dark matter, baryons, ultra-relativistic species like massless neutrinos or other, cold dark matter, non-cold dark matter species, which include massive neutrinos or warm dark matter. Now let me mention that there are other species in the code. This one is decaying cold dark matter going into dark radiation. So you find the definition of the parameters in the code, but essentially you have a decay rate such that the cold dark matter will decay into massless neutrinos, dark radiation. You have, of course, spatial curvature. You have the usual cosmological constant. And you have a fluid with which you can do whatever. As we said before, it could be dark energy, dark matter, or dark radiation. In the simplest parametrization, the fluid will be described by P over rho today, and the derivative of P over rho with respect to A. So in many papers, this is just called W0, WA. Here there is really fluid because it refers to the species called fluid. And another parameter is the sound speed of the perturbations of this fluid. So very often in dark energy model, you take inspiration from scalar fields and you set it to +1, and then the fluctuation never grow and are never important. Okay, so as we said, there is also the possibility in the code to write this as a non-trivial function, and then the code will integrate over W in order to understand what is the background and perturbation evolution. And then finally, there is a scalar field, which has lots of parameters described in explanatory.ini. In explanatory.ini, you see that you can switch between different quintessence potentials, and in principle, you can add your own. So after this short summary, let me insist on one subtlety. It's something that, okay, we didn't find a better way to code it. Maybe it will change someday, but it's a satisfactory logic, I believe. You know that you have to match the budget equation, because the budget equation is just a trivial reformulation of the Friedman equation. It has to be true. So the sum of the omegas of all species has to be 1 plus omega of curvature. So it means that you cannot specify all the omega x and omega k, because you would need to take your computer before in order to arrange for a perfect match between the terms. So to do that, you want to let the code fix one of the omegas. So one has to be unspecified. So we decided that what the code will fix would be the quantity related to dark energy. But sometimes you want to parameterize dark energy as a lambda or as a fluid or a scalar field. And in some exceptional case, in principle, you should be allowed to have more than one. So here is the logic. By default, the code will assume that omega fluid and omega scalar field are 0. So unless you pass them to a different value, it will assume that there are no fluids, no dark energy fluid, no scalar fields. And then you should not pass omega lambda. The code will adjust it. So you should pass the others, the baryons, the cold dark matter, the neutrinos. The code will adjust for omega lambda, and when you run in a terminal, it will even tell you what omega lambda had to be used in order to match this equation. Now, if you pass, by the way, if you would pass a value of omega lambda and set these two to 0, the code would complain that the input is over-constrained. So you would know that you are not following the logic. Now, suppose you want instead to have not lambda, but dark energy fluid. Then to let the code that omega lambda should not be automatically adjusted, you must say omega lambda equal to 0. And then automatically the code knows that it should go to the next level. It should assume that omega scalar field is 0, and it will adjust automatically omega fluid. Unless you have set both of them to 0, and then the code expects that he should make the complement to 1 with the scalar field. So this is the logic when you want only one of the three. When you want more than one, it also works. For instance, suppose you want to get a true cosmological constant plus a dark energy fluid. Then you will pass omega scalar field to 0, and for instance, omega lambda to 0.2, and then the code will adjust the dark energy to about 0.5. Or if you want to do the opposite, keep passing this to 0, and give a value of omega fluid, and the code will automatically adjust omega lambda to, in this case, something like 0.4. So you can still have whatever. The only way I see to improve this would be to let the user decide which species X should be adjusted automatically. So maybe one day we will have to pass all the omegas except one that will be equal to a star or a symbol. And then the code will know that it is this one that must be adjusted. For the moment, it's a little bit more rigid. It can be only one of these three. All right. So it's time to go to a different Jupyter notebook. So the Jupyter notebook that you have downloaded with a call called varying P-an is very generic. You can modify it in such a way to see the variation of your PK and CL with whatever parameter. This morning I showed the slides with delta NF. Now this P-an is a parameter that, for instance, Yacine knows well. It's a parameter describing the annihilation rate of dark matter. And it has effect on the CMB temperature and polarization. So the plot was produced by this generic module that you can easily adapt to other parameters. And we are going now to look at it. And I suggest also that you open this file and follow with me and see how it's written. Okay, so the first line gives the name of the parameters that we want to vary, and in this case it's annihilation. It's of course a name in the class syntax. So you could write here omega b in the class syntax, or whatever else, or AS, NS, okay. Then I define the array of values that I want to try in order to get this plot with different values. And in common settings, I write all the parameters that will not change when I will loop over the values of this parameter. Then I loop over the values of this parameter. And so it means I take one of these values, one after each other. And for each of them, I define an occurrence of my class that I call M. Here M means one model. I set all the parameters which were here. And now I also, with this command, I say that annihilation will be set to one of these values. I compute it. I extract the CL of my model M. Then I pass you the command for plotting. They are like in warmup.ini. And as I told you, now this could be skipped. It's now optional. You don't need to put it. So at each point in the loop, the code will plot one of these curves. And in the file that you get, everything is predefined such that you have this variation of color. Of course, you can change the color codes as much as you want. And so you see it will be very easy to generalize this plot to the parameter of your choice, and then you can use it in your paper or in your seminar. Now, this is another script doing the same, but I thought that it was worth showing it because there is something which is a little bit more complicated. So now we show the effect on CLT and on the matter power spectrum of varying this delta NF, which is the density of extra radiation on the top of photons and neutrinos. And for people who know this field of neutrino cosmology, they know that there is a little trap. You will get different plots if your convention is to vary delta NF with a different list of fixed parameter. You can vary delta NF while fixing omega CDM or omega total or the redshift of equality. There are many different choices, and they will lead to different behaviors. So in this plot, I wanted to stick to the nicest point of view. It's something that was developed in a paper by Hugh and Knox a few years ago. And they say, no, we should fix this and this quantity because this is what the CMB determines. And then we see directly, for instance, how changing delta NF changes the damping scale in the CMB. But why is it a bit more complicated? It's because in order to get this figure, while varying delta NF, we must vary all other parameters in the class inputs. So how is it done? Our goal is to fix the redshift of equality. And the redshift of equality is the density of matter over the density of radiation. Here we are varying the density of radiation by a 1 plus C NF, where this C is our universal coefficient that you can compute, which will be actually computed automatically in the code. Okay, so when we vary NF, we increase the density of radiation. If we want to keep the same ZX, we must increase omega M by the same amount. But omega M is omega B plus omega CDM. We want to fix omega B because it's given by the CMB. And we want to increase omega CDM in such a way that omega M increases proportionally to this. So we will need to do a bit of algebra. And we will need to change H, because H in this basis is given by this relation. If omega M increases, then H will change. So if you're not very familiar with this physics, this probably seems very cumbersome to you. But I just want to show you what kind of extra line you have to write if you play this kind of game. So now I'm going to define an array of model. You see, at some point, I will have an array of model with an index I, because in this script, which is a bit more elaborate than the previous one, I want first to have a loop in which I compute all my models. I keep all of them in memory, and in the next cell, I will plot all of them. So it's nice, because if I want to change the presentation of the plot, I don't need to recompute all the models. This is why, instead of overwriting always over the same class M, I now have an array of models. So now I only show the important lines. There are many lines which are the same in all the scripts and that I don't show again. I loop over the value of my delta NF, which is in fact NUR. And for each value, I do the algebra corresponding to these lines in order to find the correct omega CDM and the correct H at each step. CoF is this factor C, and if you look, it is evaluated somewhere above in the script. Okay, now for my index I create M of I. So M of I now will store one of the cosmologies. For M of I set the command parameters. I set NUR, I set omega CDM and H to these values. I compute, and now I have all my models stored in memory. And in the next cell, we will do another loop, and inside this loop, we will have the commands to extract the CLs, the PK, and plot them in the figure. And this is how you get the figures that we saw before. And this is something that you could not do nicely without a Python notebook, because before having Python notebooks, I was doing everything from the terminal, and I had to compute manually all these values inside the loop. It was horrible. Okay, here is another example of script. If you are fans of neutrino cosmology, you will find it nice. It shows the difference between the matter power spectrum. I see there is a missing label here. This should be the ratio of the matter power spectrum with massive neutrinos divided by the matter power spectrum with massless neutrinos. But each curve shows a difference between having the matter power spectrum with neutrinos ordered with a normal hierarchy or with an inverted hierarchy. So it's really the relative difference between normal and inverted hierarchy for common values of the total neutrino mass. So these are 3 values of the total mass, and for each of them, it's a relative difference between normal and inverted hierarchy. And you see that these differences are very small. In fact, most people believe that this difference will be essentially impossible to detect even with future experiments. 0.02% on the matter power spectrum already on nonlinear scales. And for an optimistic neutrino mass, this would be very difficult to measure. So how do you get this plot? It's again a script where you loop over values of parameters. But here, because you are in a Python script, you can do something sophisticated, which is to call a function, to define and call a function giving you neutrino masses. So in this example, it's also a way to see how to set things with neutrino masses. I assume, well, I don't assume, the notebook contains a function, get masses, which takes as an input the delta m square atmospheric and solar, the total mass and the hierarchy. And for these parameters, it will spit out 3 different values of the mass. So the hierarchy can be set to normal hierarchy or inverted hierarchy. Now we do a loop over the total mass. The total mass will be vary from 0.1 to 0.13 electron volt in this example. And first, I call my get masses function for the normal hierarchy, and I have an array of 3 neutrino masses. I define a class that I call nh. I set the command parameters, and then this is the command that you will use to set the variable m_ncdm to a list of 3 values, because m_ncdm can be set to 1 value when you have only 1 non-cold dark matter species. But if you have 2 or 3 or 4 non-cold dark matter species, m_ncdm is supposed to be a list of 1, 2, 3 values. So here, by splitting, by writing these values of m1, m2, m3 as strings separated by commas, we create on the right-hand side a list of 3 values separated by comma, and this is the input that the code wanted. Now we call class, and class will get the exact result for this mass splitting. Now you want to do the same for the inverted hierarchy. You call the same function with inverted hierarchy. You go through the same steps, and you have your 2 cosmologies with NH and IH. And I forgot if it's shown in the next plot, but now, like in the other scripts, once you have it, for NH and IH, you call getLength CL, and you call the pk function, and you get the results, and then you can compute the relative difference. Okay, now let's go to another notebook illustrating what you should do if you want to play with tensors. I'm trying I have selected notebooks that show you the basic functionalities of the code. So now we will have for the first time tensor modes, and we want to do the famous plot where the different colors stand for temperature, E polarization, B polarization. The fact of being solid or dashed stands for scalars or tensors. And you also have the contribution from the lensing of the B modes here. Okay, so to get this, I have another script here called clst.py. And the idea is that we will first run class in order to have our figure with scalars only, then with tensors only, and then we can do things, and then with scalar with plus tensors. And then we have all the information to show all the curves of the previous plot. So for scalars only, in my class M, I set parameters. I ask this time for the variable modes that you have never seen so far in the course. We set modes to S for scalar. Okay, we must pass also a value of the scalar tilt. We ask for a computation up to 3000. And in order to get the previous plot, I was interested in the unlensed CL of the scalar modes. And to get the unlensed CL, instead of CL lensed, you have to call rho CL. Rho CL means CL unlensed. Then to get the curves with a tensor, so there in the little dot, they are plotting comments that I don't show for concision. And then I want to get the tensor contribution. And it's about the same, except that for the modes, I put T for tensors. And for the amplitude of my tensors, I pass R, which is a tensor to scalar ratio. I pass it here equal to 0.1. And I pass NT. NT is a tensor tilt. It's set to 0. Okay. I should then run the code. So there should be a m.compute that I have not written. And then I extract my tensor CLs with a rho CL again. And finally, I run with both modes at the same time. And in this case, I put a list ST, so I will get both scalars and tensors. I need to still pass a value of R, a value of NS, a value of NT. I get the rho CLs, and I get also the lensed CLs. It didn't make much sense to lens the other ones, because what is lensed is always a total contribution. So plotting the lensed scalar-only contribution would have not made much sense in the previous plot. Okay, once you go through all these steps, you have all the information to get the curve that was on the previous slide. Okay, now this is another example in which you try to split the CLs of temperature into individual contributions. So as we said before, the total length is a black, the total unlength is a red. And this red comes from different contributions. The intrinsic temperature with its Sachs-Wolf contribution, which is the most important term, the early integrated Sachs-Wolf, the late integrated Sachs-Wolf, and the Doppler contribution. And there is a fifth one, which is a contribution from the back reaction of polarization that you can also get with class, but I've not shown it on the plot because it's so small. Okay, so it can be interesting to show a plot like this because maybe you are going to publish a paper on a new cosmological model which has an impact on the CLs, but you are not completely sure if this impact will be at the level, for instance, of the late integrated Sachs-Wolf because it's a dark energy model, or at the level of the intrinsic temperature. You are not sure themselves. You want to convince yourself, and you want to convince the people reading your article by showing it explicitly. So you can compute this decomposition in lambda CDM in your model, superimpose the result, and say, you see, my model affects the CLs only at the level of, say, the early integrated Sachs-Wolf. So it can be very convenient. You might feel disturbed by the fact that the total curve doesn't look like the sum of the other curves. This is because there are cross-correlation terms, which are not shown here. So for instance, the red curve is the sum of these four other curves plus all the cross-correlation between pairs of terms. And it's because we have not plotted here the cross-correlation that you have the impression that, for instance, if I sum these three values, I will not get this value. Okay, so how do you plot this? You use an input variable, which is called temperature contributions. So as usual, I define a class, I set lambda CDM parameters, I compute, and first I'm going to compute the full CLs in their unlensed version and lensed version. So these two gives me the red curve and the black curve in the previous slide. Then, okay, no need anymore to clean. Then you want to call class another time, this time only with the temperature and Sachs-Wolf contribution. It was a magenta, it was a cyan curve before. So you have this variable, temperature contributions, which is documented in explanatory.ini, which expects a list of effects. And the effects belong to this category: temperature and Sachs-Wolf, early integrated Sachs-Wolf, late integrated Sachs-Wolf, Doppler, and there is a fifth one called Pol for polarization. And if I would put the list of the 5 here separated by comma, TSW, comma, EISW, comma, etc., I would get the same as before. But I'm allowed to put only 3 or only 2 or only 1. So here we put only 1, we compute, and we extract the contribution to the CLs from this term. And then the notebook does the same with the early, the late integrated Sachs-Wolf, and the Doppler, and then plots each curve on top of each other. Okay? Now let me go to another example. Okay. We have shown example only with CLs and pK. There are not only CLs and pK in life. There are background quantities, thermodynamical quantities, transfer functions, etc. So here, let's assume that we want to reproduce a plot from the book of Scott Dodelson on modern cosmology. It's a famous plot comparing the luminosity and comoving and angular diameter distance as a function of redshift for 2 cosmologies, lambda CDM and Einstein de Sitter. So how do you get this plot from class? The trick is that, by the way, it's in distances.pi. The trick is that class also stores the background and the thermodynamics variables. You can extract them after running class computes. So here we create an instance of class called LCDM for lambda CDM. We set cosmological parameters, and okay, we won't control on omega B and omega CDM because it's important to be sure of their value for this example, but I don't pass the other because I'm happy they are fixed to whatever reasonable value. So you see that this will be lambda CDM, omega lambda will be automatically adjusted to 0.7. I compute, I have all my results stored here. I do the same for the Einstein de Sitter model. I compute, and I have everything stored here. So we didn't pass an output field. Normally, we were using TCL, PCL, LCL, and PK. But we don't need any CL or any PK. So we just don't pass anything in output. And the logic of class is that when there is no output requested, only the background and thermodynamics module will be evaluated. So actually, when you call class without this output field, it lasts only a few microseconds because these modules are extremely fast. Now, this is what you get in the script. This is first a cross-check that I've added it because I think it's interesting, but it was not necessary in order to plot the Dodelson result. We want to check that omega lambda was set correctly. If I go to the previous example, in this case, we said omega lambda will be adjusted automatically to 0.7. Well, not exactly, because in the budget equation, you have a small contribution from radiation. So what should be 1 should be omega CDM plus omega B plus omega radiation plus omega lambda. By default, radiation is the normal photons, the normal massless neutrinos. It contributes by a very small amount, but then it means that omega lambda should not be exactly 0.7, but a little bit less. In the other case, I didn't want to bother computing omega of radiation, which is 10 to the minus 5, so I wrote this, but my omega lambda should not be exactly 0. It should be a slightly negative value compensating for omega radiation such that the total is 1. Okay, so when I coded this, I had a doubt. Is the code doing what it needs to do? Will it fix omega lambda to something negligible but negative? And we should check it because there is a very useful function in the wrapper, which is get current derived parameter. And as you shall see, when class runs, it produces a long list of so-called derived parameters, and you can always extract any of them if you need them. In this example, I want to be sure of what was the omega lambda that class has determined by itself. So the results of my Einstein de Sitter are stored in CDM, and I call the function getCurrentDerived parameter of CDM for the name omega lambda. And the result will be a dictionary with a key, which is omega lambda, and its value. And indeed, it's a small negative value. It's what I expected. It will just compensate for omega radiation. And if I want omega lambda, I can use this command to be sure. Okay, so the code behaved as we expected. And if we wanted to be super precise, you see that we should decrease a little bit, for instance, omega cold dark matter, such that this would really be 0. But anyway, you will never see the difference between 0 and 10 to the minus 4, so it's not very useful. Now, how we introduced here this nice function, getCurrentDerived parameter. And this function has many, many possible entries that I have tried to group here in one slide. So all these are parameters that you did not pass in input. Probably you don't know what are exactly their values, but they are determined by class during the run. Some are determined in the background module, some in the thermodynamics module, and some in the primordial module. In the background module, class will always store the omega and h in different formats, some h variables. This will be the mass of neutrinos in electron volts. Maybe you don't know it because you passed omega of neutrinos, of massive neutrinos. Then the mass in electron volt was computed for you by the code. And this will give it to you in electron volt in some other units. N effective will be determined for you by summing up the contribution of the massless neutrino and the massive neutrinos. Omega m by summing up all the non-relativistic species. So it's interesting to extract them after class compute. At the level of thermodynamics, first there are some variables that you can be interested to compute. If you passed to the code the optical depth to reionization, then it will determine automatically the redshift of reionization, and you can extract it here. But it's your choice. You can instead pass to class the redshift of reionization, then it will compute tau reo, and you can extract it here. This is the 100 theta s that we mentioned before, the angle under which you see the sound horizon. The primordial helium fraction was determined by the BBN module, so you want to know the answer. And there are a few other ones like this. This is the number density of electrons. I forgot the details. All this is documented. Okay, and then also you have quantities which are calculated at recombination, like the redshift of recombination, the conformal time at recombination, the sound horizon at recombination, the angular distance at recombination. What you should know is that every time that you see a variable starting by r, it's a comoving distance, and by d, it's a physical distance. So you have, for instance, rs rec and ds rec, the sound horizon at recombination, comoving or physical, and you know that they will differ by a factor of the scale factor at recombination, a rec. The same for the angular diameter distance. You have the comoving one and you have the physical one. And there are many others like this. You can get the same quantities not at recombination, which is the peak of the visibility function of the photon, but at baryon drag, which is when baryons decouple from the photons. You know that it takes place a little bit later. And for instance, in order to fit a BAO result, what you want typically is a comoving sound horizon at the time of baryon drag time. D is for drag. So this is used a lot in BAO likelihoods. At the level of primordial perturbation, there are a number of derived quantities, like say sigma 8, for instance, and okay, many others. And actually, there are other derived quantities related to inflation and isocurvature mode that I do not show. So in the next script, you will see how by playing with derived parameter, we extracted some useful information for the plots. Okay, so I'm still in my script distances.py. I've not finished to explain it. I didn't tell you how to extract background quantities from the class. Okay, so we have seen functions for the PK, we have seen functions for the CLs. There are also other functions for the background and the thermodynamical evolution. For the background, it's get background. So I have already computed my lambda CDM cosmology and my Einstein de Sitter cosmology. For each of them, I do a get background, no argument needed, and the code will produce a big array that contains the evolution of 4 background quantities with time. And again, probably I forgot the syntax of this. So I do a view keys, and people pointed out this morning that if you use Python 3 and not Python 2, it's not view keys, but just keys. And that's nice because I realize that any of these 2 arrays are dictionaries with many entries, and you can see these as the name of different columns. So for instance, there is a column for conformal time in megaparsec. There is a column for redshift. There is a column for the critical density, for the density of baryons, of photons, gamma, of lambda. What is this parenthesis dot? It's because I told you that the class densities are not the true densities in gram per centimeter cube, but are 8 pi j over 3 rho in megaparsec to the minus 2. This is what the code is giving you. And this is a shortcut for the 8 pi j over 3, so that you remember that there is a prefactor. Okay, so we have here the luminosity distance. We have the comoving distance. We have the angular diameter distance. We have the proper time in gigayears, the linear growth factor, the density of ultra-relativistic components. So once I have this array, I'm free to plot my quantities using as an x-axis the redshift, or the proper time, or the conformal time. So I have all what I need in order to do the plot of Doddelson now. I will just plot the contain, for instance, as an x value, I will take, as an x-axis, I will take z. As a y-axis, I will take luminosity distance, and I will get one curve. Okay, so with get background, you get a table of values, and if you want to interpolate it, you still have to write the interpolator. But the code also contains some predefined interpolation functions of background quantities. Suppose that I want directly my luminosity distance at a redshift z. Then instead of doing a get background, finding where I am in the file and interpolating between 2 values of z, I will go much quicker if I call LCDM dot luminosity distance at the redshift of my choice. And the result will just be one number. So it's a more economic way in this case. So we have several functions like this of z, luminosity and angular distance, Hubble rate, the linear growth factor, and sigma of R and Z can be also called. I wrote it here, but in fact, sigma is more related to perturbations, not to backgrounds. I should have put it on the slide on the background. You can directly, if you have computed perturbation, you can directly call the function dot sigma of R equal, for instance, 8 and Z. Okay, so I think this is the last slide on distances. And now we try to see what is in this Python notebook for thermodynamics. So for thermodynamics, it's the same. Here in this example, I want to show the visibility function G. And the part on the right with the reionization peak has been multiplied by a factor, otherwise the reionization peak would not be visible on the same scale as a recombination peak. So how do you plot this from class? Well, again, with a simple script, it's thermo.py. It always starts with the same steps. And this command will be useful to show the two vertical lines before. Before we had two vertical lines that were showing the time of recombination and the time of reionization. And I will get them after computing everything with a get current derived parameter. And now I ask for tau rec, which is a conformal time at recombination, and conformal age, which is the time today. I didn't ask for tau reo because I knew it from my input. Okay, so then I call the function get thermodynamics. It's like get backgrounds for the thermodynamical quantity. So after doing this variable thermo is a big array containing the evolution of all interesting thermodynamical quantities. And if I do a keys or a view keys, I see the name of the different columns. This is the redshift. This is the ionization fraction, the visibility function, the conformal time. Kappa prime is the Thomson scattering rate. Tau d is the time of the baryon drag. TB is the temperature of the baryons. CB square is the sound speed square of the baryons. So I have this big array, and I can play with the columns in this big array in order to output my quantities. I'm sorry, tau d is not the time of baryon drag. It's a function of redshift. It's the baryon optical depth. And the time of the baryon drag is when this baryon optical depth crosses 1. It happens at a redshift of 900 something. Okay, on top of this derived parameter, again, I have functions of z. I can directly extract the ionization fraction or the baryon temperature at the redshift of my choice in order to do some plots. So this was for thermodynamics quantity. Now, for the primordial spectrum, there is no notebook here. And I don't think there are people here who are very much specialized on inflation. So I will skip this slide in order to try to finish more or less in time. And I show you now another example. So this, you have now the script in order to produce this plot. It's called onetime.py. This is typically the kind of plots you would do when you want to explain, for instance, CMB physics. But you could have a version of this to explain large-scale structure formation. So the logic of this plot was to choose a time, and here it was the time of photon decoupling, and at this time show what is the amplitude of the transfer function for many components. So the time is fixed to tau decoupling, and we show the transfer function as a function of the wave number k. So let's comment only the first plot in which we have all these transfer functions for different quantities. So how did we produce this with a script? There are also some characteristic times like the Hubble crossing time or the time of crossing the sound horizon. So we produce it with a new syntax, which is here, always the same step, command settings. But there is something new here. You have never seen so far MTK and VTK. You have seen MPK, it was a matter power spectrum. Now you have MTK and VTK. Now I am asking class to keep memory as a source function of the matter transfer function, which are all my density fluctuation delta normalized as a transfer function to r equal 1. And with VTK, I ask class to keep in memory all the velocity transfer function, which are theta in the formalism of Mayen-Bertschinger. You see also a variable you never saw before is a gauge. I wanted to do my plot in Newtonian gauge, and the default is a synchronous gauge. So not to use the default, I have set gauge to Newtonian. And then I want my matter and velocity transfer function to be stored up to a maximum value of z. If I don't precise to which value, the code will be lazy and will store this value only up to a redshift of 0, so only today. So I don't want the code to be such lazy. I want it to store the quantity until the redshift of recombination. And the redshift of recombination is not shown here, but in the script, it's extracted automatically by doing a first run of class and reading this from the getDerived parameter function. So now, with this input, the code will store the matter and velocity transfer function between redshift 0 and the redshift of recombination. I execute class, and then I want to extract this transfer function, and it's done with getTransfer. GetTransfer takes an argument which is a redshift, and so one time will store all the transfer function of all the species at the time corresponding to recombination. I forgot what is the syntax for this, so I do a dot keys or dot view keys. And I get a list of all what the code has stored. So there is one column for k, of course, because we want to plot things as a function of k. And the other column are the metric fluctuation. The t are the theta, in fact. So they are the theta, the velocity divergence of the different species. The d are the delta. So it's a density perturbation of the different species. So I have them for ultra-relativistic, cold dark matter, baryons, photons, and the total, and the same for delta. Okay, so now I remember the syntax. So I will put all the values of k in an array by calling one time with the key for wave number. And for instance, if I call one time of dj, it will store all the value of delta gamma, the fluctuations of the photons. But what many authors call theta 0 is a monopole of the photon and is 1/4 of delta gamma, because delta gamma is 4 delta t over t. So I multiply by this factor to get theta 0. I extract the metric fluctuation phi, and I am ready to do the plot before. But this would not have worked if we had forgotten to put mtk. Mtk is enough if you don't want the thetas. So we had to put mtk, and we had to put zpk equal at least to the value at which we wanted the output. So the number here should be bigger or equal to the number here. Okay, before the exercises, you will see there are 2 more scripts I want to show you. So this will be the first 5 minutes of the next session. And then I will propose you a list of simple exercises in order to practice with class without modifying it, since the modifications are for tomorrow. Thank you.